In this video, we'll be describing how to balance chemical equations. And so we start off with just kind of looking at what a chemical equation is. So a chemical equation describes what is happening in a chemical reaction. It describes how many of reactants there are, how many products there are, what the ratio of one to another is. It also describes the changes that we see on the atomic level. So, for example, I look at sulfur trioxide, it reacts with water, and it forms sulfuric acid. I take that sulfuric acid, react it with iron 3 oxide, and I get water and iron 3 sulfate. Now, another piece of information that we can get from the chemical equation is a state of matter. So S refers to solids, L refers to substances that are in the liquid phase, G refers to gases, and AQ refers to anything that is in aqueous solution. And what we mean by aqueous solution in particular is we have something dissolved in water. That's what aqueous means really for us in this scenario here. So when we talk about aqueous sulfuric acid, we're talking about sulfuric acid that has been dissolved in water. When we talk about aqueous iron 3 sulfate, that is iron 3 sulfate that has been dissolved in water. And as an aqueous solution, it is going to have slightly different properties. Now, when it comes to balancing chemical equations, what we have to take into consideration is something that you already know, and that is the law of conservation of matter. Law of conservation of matter, if you remember all the way back to our fundamental laws way at the beginning of the semester, we know that for any process, chemical or physical, that matter cannot be created or destroyed. And so the law of conservation of matter, in our particular case, looking at chemical reactions, means that every single atom of every single element has to be present both before the reaction began and after the reaction concluded. And that's why we have to have balance in our chemical equations. We can't just have any kind of arrangement of reactants and products. There has to be a balance. There has to be a leveling there. Now, some important things to recognize. One of the most common mistakes that students make is that when they get stuck, they improvise. And one of the ways that they improvise is by changing subscripts of compounds to get equations to balance themselves. And that's a problem because, well, that's not how it's supposed to be. And when we change the subscripts, we actually change the identity of the compounds themselves. So when I say that something is H2O, that means that there are 2 hydrogen atoms and 1 oxygen atom for every molecule. If I change that, say H2O2, I'm no longer talking about water. I'm talking about something called hydrogen peroxide. Water, on one hand, is a essential component of your body, and without it, you will eventually die. Hydrogen peroxide is something that if you drink it, you will die rather quickly, especially if you get a high enough concentration. So there's a real distinction there, and changing the chemistry, changing the compound identity does play a significant difference. So when we're balancing equations, we're going to use coefficients. Coefficients are going to be what we use to signify the number of molecules that are there that are going to balance the equation. And so, again, the distinction here, putting a 3 in front of iron means that I have 3 individual iron atoms in the reaction vessel, as opposed to Fe3, which would imply that I've got some sort of molecule that has 3 iron atoms attached to it, and every one of those molecules would have 3 iron atoms. It's a subtle difference, but it's an important difference when we start looking at how to use these. So when it comes to balancing equations, if you are new to balancing equations, I recommend using something called the atom economy method. In the atom economy method, what we're going to do is we're going to split the reaction in half. We're going to keep track of all of the different reactants and products. And then as we change coefficients, we're going to track those changes until we get to a point where the atoms on the reactant side and the atoms on the product side are all equal for all of the elements. Now, this process does take some time to do, but as you get used to it, as you start to pick up on some of the tricks, on some of the things that make it easier, it does get easier for us to work on. And we will find that it is easier to do. We can eventually go away from the atom economy method and go toward what is called balancing by inspection, where you just kind of know where the numbers are going to go and then you do some quick math in your head. But if you're new to this is the way to start to at least get your feet in the door. Now, that said, there are some ways that we can make the balancing easier on ourselves. For one, we can always leave hydrogen and oxygen for last. Hydrogen and oxygen are found most commonly. They're of the inorganic elements, they're the most common, and they tend to be in multiple compounds at the same time. So, for our purposes, it's easier to just keep them for the end and hope that once we balance everything else, they'll kind of be easy to figure out how to do. The other place where we can do some work is with clustering. Now, this is particularly true for replacement or displacement reactions. Single and double displacement reactions, or single and double replacement reactions, depending upon what source you're looking at, tend to have polyatomic ions in common. So you'll have nitrate ion on the reactant side and the product side. You'll have oxalate ion on the reactant side and the product side. And if you notice that, take advantage of it. Instead of separating the nitrate into nitrogen and oxygen, keep it together. Track nitrate ions on the reactant side and nitrate ions on the product side. And if you do that, chances are things will kind of work themselves out. And you'll be able to balance a lot more quickly. So let's take a look at some examples here. So in this first example, we've got an iron oxide ore here, iron 3,4 oxide, reacting with hydrogen to make iron and water. Now, this is an example of a single replacement reaction, but we can't use the clustering that we talked about in the previous slide because there are no polyatomic clusters in this. But what we can do is split it down the middle, and I've got iron, 3 of them. I've got oxygen, 4 of them. I've got hydrogen, 2 of them. And on the product side, I've got 1 iron. I've got 1 oxygen. And I've got 2 hydrogen. So if I look at it from this perspective, one of the reasons I want to keep it like this, I want to keep everything aligned. So I'm going to look across and see, okay, irons are not balanced, oxygens are not balanced, hydrogens are for the moment, but let's see where this takes us. Now, one thing that we can look at, one trick I can give you automatically, if we see compounds that have multiple subscripts in them, there's usually a pretty good indication that these are going to be used in making coefficients on the other side. So what I like to do, if I see multiple subscripts on one of the reactants or products, I'm going to use that to balance the other side automatically. So there are 3 irons in this compound. I'm going to make this a 3, so that subscript is going to come over and make a coefficient over here. I have 4 oxygens. I would need 4 waters to balance that. So that subscript is going to become a coefficient over there. I've now changed coefficients, so I need to change my numbers. I now have 3 irons. I now have 4 oxygens. And in the process of changing this, I've changed my hydrogens as well. I now have 4 times 2 for a total of 8 hydrogens on the product side. So this subscript shift has balanced my iron and has balanced my oxygen, but has thrown the hydrogen out of balance. Luckily, pretty easy fix. Pretty easy fix here. All we need to do is put a coefficient of 4 in front of the hydrogen. That'll make 4 times 2 for 8 total hydrogens on the reactant side. And so I can look now and see that I've got even irons, even oxygens, even hydrogens, even all the way around. We've got ourselves a balanced chemical equation as is written right there. Again, we split the equation down the middle, reactants on one side, products on the other, and we're going to break it down into carbon, hydrogen, and oxygen, the 3 components here. And again, notice I'm lining up the elements on each side so that I can compare directly. And so one thing to notice about combustion reactions like this is since we have oxygen in multiple places here, we have to be sure that we're remembering to add. And so the amount of oxygen on the product side isn't just the amount in the water, and it isn't just the amount in the carbon dioxide, but it's actually the sum of them. Now, if we apply the characteristics that we looked at last time, again, I've got a pair of subscripts here. If I take those over and turn them into coefficients for the 2 products, that will help with some of the balancing. Now, small mistake here. I don't actually need 10 of these. I just need 5. 5 times 2 gives me the 10 that I seek. So my carbon goes from 1 to 4. My hydrogen goes from 2 to 10. But my oxygen goes from 3 to, now I have 8 in carbon dioxide and 5 in oxygen. 8 plus 5 is now 13. Now, this provides us with another dilemma. I've got my carbon and my hydrogen balanced as is. Problem is, I don't have a way of getting 13 oxygens on the reactant side, because every single one of my oxygen molecules has oxygen coming out in pairs. So I'm always going to get an even number of oxygens. So how do I get 13 here? Well, the answer is actually really simple. I can do it really one of 2 ways. I can either cheat the system, and if I cheat the system, I could put in a fraction here, 13 halves or 6.5, and 13 halves times 2 would give me the 13 that I need, and I would have a balanced chemical equation. And if we're dealing in large quantities, moles of each of these substances, that's really not a problem. However, mathematically speaking, it does become a problem if I start thinking about things molecularly. After all, what does half of an oxygen molecule look like? Answer is, really don't know. It doesn't really exist in that kind of way. So what you'll see most people do is instead of using a fraction there starting this over, what they'll do is they'll just double everything. And so what that means is if I start with 2 of the butanes, 2 C4H10s, and take it from here the rest of the way, carbon, hydrogen, oxygen, I now have 2 times 4 for 8 carbon, 2 times 10 for 20 hydrogen, and still 2 oxygen at the start. If I carry that over onto the other side, my 4 carbon dioxides now become 8, my 5 waters now become 10, and so once I take care of those, 8 carbons, 20 hydrogens just like before, 8 times 2 is 16 plus 10 more, 26 oxygens in total. And now 26 is an even number. I can balance and get an even number on the other side with a 13 there. And that's what balances this equation. And so now I have even carbon, even hydrogen, even oxygen. I've got a balanced chemical equation that way. So this methodology and combustion reactions are notoriously the most difficult in this domain. But this kind of methodology is useful. So if we're dealing with molar amounts, if we're getting into stoichiometry, yes, you could use fractions there. However, if we're talking about molecular kinds of quantities, individual atoms, individual molecules, you have to have whole numbers here because there's no such thing as half of a molecule. Let's look at another example. Here's an example of a double displacement reaction. And what's useful to us about a double displacement reaction is we see that we do have some commonality. Sulfate ion is present both in reactant and in product. So when I'm tracking instead of tracking individual sulfurs and individual oxygens, I can track sulfates. And so if I follow this all the way through, one of the other nice things about double replacement reactions is that they're usually pretty easy to balance. You can see already, I've got 1 sulfate on each side, I've got 1 barium on each side. The only things that are out of balance are the potassiums and the chlorines, which happen to be in the same molecule on the product side. And so they're off by the same amount, which means they can be reset by the same amount. And that amount here is just a 2. 2 KCl's makes 2 Ks and 2 Cl's. And now those are all balanced as well. I've got a balanced chemical equation. So for these last two, I'm going to give you the answers here in about 15 seconds. What I want you to do, pause the video and try to balance these on your own. If you need to break it out and get into the atom economy method, go ahead and do so. If you're feeling confident you can do them just by inspection, that's fine as well. But in 15 seconds, I will reveal the answer. So if you want to do that, go ahead and pause now. Okay, we're back. And here are the answers for the 2 example problems. Now, both of these were combustion reactions, and combustion reactions are probably the most difficult ones to balance. But if you can master them, if you can kind of get through behind the tricks of them, you can really balance anything. So in the first one, very similar to the combustion problem that we just did, you had to double everything. A little trick that you can look for when hydrocarbons are burning, um, if you have an even number of carbons, generally speaking, that's usually a sign that you're going to have to double everything. It's not always the case, but if we're talking about alkanes, so simple saturated hydrocarbon burning, butane, octane, decane, those kinds of things, they're going to follow that same pattern. You're going to double the hydrocarbon, and then everything else will kind of shake out from there. This one was probably the more difficult of the two. Um, you have to break out the atom economy there, because what you'll find is that the kind of the key aspect is recognizing that the hydrogen is an even odd split over here. You have 3 hydrogens in the ammonia, you have 2 hydrogens in the water, so you're going to have to go the lowest common multiple route, 6, to get them there. Once you do that, you run into the same problem with the oxygen, so you end up having to double everything.